This video teaches you how to calculate expected loss in Python. I'll teach you how to do it with the keyboard and without using the mouse. Subscribe, hit the like button, and buy my books. Links in the description below. Let's get into the video. To open Google Chrome, press Windows key 9 on the keyboard. Alt E is in Echo, B is in Bravo. Arrow up to get to Google Collaboratory. Tab over to get to expected loss. Let's begin. The first cell of code is really to import the libraries needed to run this code. So we'll import numpy, as N is in November, P is in Papa. That's short for numerical Python. That's what numpy means. Then from SciPy decimal stats, we'll import the inverse Gaussian function, which we're going to use in our probability of default algorithm. And from SciPy decimal stats, we're also going to import norm for the log normal distribution. Control Enter to run this. And it works. Arrow down to get to the next cell. Next, I'm just going to create the variables that I need to calculate the probability of default. Remember, expected loss equals probability of default times loss given default times exposure at default. The three key variables you'll need in the probability of default calculation are mu, lambda, and T as in tango. T as in tango is the life of the loan, essentially. So since I've set it equal to 4, the loan has a life of 4 years. Mu is the average. Then you have lambda as well. Control Enter to run this. And then the next line of code, I'm going to create a variable to calculate the probability of default, and we're going to use the inverse Gaussian function today. Traditional credit managers might look at the 5 C's of credit, so they'll look at cash flow, capacity, collateral, credit rating, and the character of the borrower. We're not doing that today. We're taking a more of a quantitative approach to calculating expected loss, and we're going to use the inverse Gaussian function to do that. So in other words, the probability of default, I'll create a variable for that, P as in Papa underscore default. That's going to be 1 minus the cumulative distribution function of the standard normal distribution for the inverse Gaussian function with several key arguments. Of course, the life of the loan, mu, loc, I'm going to set that equal to 0. And to scale it, I'm going to use the lambda underscore variable, which is another key argument. Control Enter to run this. Now let's print the probability of default. We can see it's just under 42%. So this is some really high risk loan where the company is in distress, having solvency issues, something of the sort. This is not a standard loan that a bank would make. This is a distressed type of loan. But we can print that. So we can say print F as in Foxtrot, then in double quotes, the probability of default within the number of years is probability of default within the dictionary, which is what those curly brackets are. And so you press Control Enter to run this. You can see it prints the statement. The probability of default within 4 years is 41.89%. Let's say lambda was only 1.7. I could rerun this. And if lambda is lower, I have a much lower probability of default. 28.64% is still quite high. I I mean, you would really want to bring this lambda down to, let's say, 0.5. Control Enter. Now we're getting a 6.53% probability of default, which is actually still quite high. Let's say I cut lambda in half again. Control Enter to run this. Now we have a loan with a 1.69% probability of default. That's more reasonable. Banks will make certain loans at origination that have that type of probability of a default. Next, I'm going to create the recovery rate and volatility variables for the loss given default algorithm. So recovery rate, for now I'm setting that to 20%. In other words, the lender makes a loan of $100 US, and under a 20% recovery rate, in the event of a default, they would get back $20. So maybe the loan was secured against $20 of collateral. Implied volatility 0.4, that's the volatility of the underlying asset. Set that quite high to 40%. Control Enter to run that. And then we're going to calculate the loss given default now that we have the recovery rate and volatility variables. And to do that, we're going to do the inverse of the standard normal cumulative distribution function to calculate the Z as in Zulu score, the Altman Z score. And probability P underscore default, which we had created earlier, is going to be a key argument in there. Expected loss given default is 1 minus the recovery rate of 20% times the Z score, the Altman Z score, times the implied volatility. That gives us our loss given default. And then let's print the loss given default. Again, similar code as before. Print tuple, F as in Foxtrot, quotations. Type in whatever you want to type in. I'm typing in the expected loss given default is, and then have your dictionary referring back to the variable. And then, since to let it know it's a tuple, you do the colon decimal 2%. Control Enter to run this. The expected loss in this case, given default, is almost 68%. So in other words, if there is a loss, if there is a default on a $100 loan, the lender expects to lose almost $68, right? They expect to lose $67.89 in this example. Next, we're going to define the parameters for the exposure at default algorithm. So we're going to create a hypothetical outstanding balance variable. I'm just setting it equal to $100,000 US, and then a credit conversion factor. I'm setting that equal to 0.5. Control Enter to run that. And now we're going to have to calculate the exposure at default. Exposure at default is just the product of the outstanding balance and the credit conversion factor variables that we just created. Control Enter to run that. And then finally print that. Just like before, the exposure at default is 50,000. So at the time of default on a $100,000 loan, the lenders has 50,000 of exposure, let's say. Now, finally, we can calculate the expected loss. We've created the probability of default variable, the expected loss given default variable, and the exposure at default variable, so we can create a fourth variable called expected underscore loss and set it equal to the product of the first three variables. Control Enter to run this. And then finally, we're going to print that. The expected loss in this case on a $100,000 loan is 575.06. That's pretty low and pretty reasonable. If it was a bank making the loan, they might hold loan loss reserves of, in this case, almost $600 against the $100,000 loan. That'll be a liability on their balance sheet. And under the CECL accounting standard, current expected credit loss, the bank has to put up the full loan loss reserve for the life of the loan up front. Let's say that lambda was equal to 3, we'd get a much higher probability of default and therefore higher expected loss. Control function F9 key to run it, and you can see the expected loss went up to 872.83, and the probability of default is now 45%. Again, this is a distressed loan, not normally a loan that a bank would originate on the primary market, but it's a distressed loan that a distressed debt investor might buy from a bank, that sort of thing, right? And let's say there's time equals only 1 year, the probability of default actually goes up, which is counterintuitive to a lot of people, but that causes the expected loss to go way up. Now you have a loss of 16374.56. So take this knowledge into the marketplace to be a better credit risk manager, better understand credit, better understand Python, and understand these relationships, and how the inverse Gaussian function is used to calculate probability of default, which is then plugged into expected loss. Have a great day. Thank you for watching this video. Please subscribe to my YouTube channel, hit the notification bell, hit the like button, leave a comment below, and please buy my books. The links to those will be in the description of this video.